So in this chapter we're talking about extraction of metals, and when we extract metals, metals are extracted from what we call their ores. Their ores are the raw form of the metal obtained from the earth. So each metal we're going to talk about has a specific ore which we get out of the earth in a raw form, and then we do something to it in order to get the pure metal. So the method of extraction depends on which metal are we talking about, because it depends on the reactivity of this metal. So when we look at the electrochemical series, there are two main methods of extracting metals. Either we use electrolysis or we use reduction with carbon. Reduction using carbon. You should realize that electrolysis is an expensive process, so we're going to choose it only when we cannot use reduction. Since most of the ores are in the form of the oxide, then reduction with carbon can be done if the carbon is more reactive than the metal. For example, we can use carbon to reduce zinc oxide. So carbon will react with zinc oxide because carbon is more reactive than zinc. Carbon will react with iron oxide because it is more reactive than iron. It can react with tin oxide if needed. But it cannot react with the oxides of anything that is more reactive than it. So for example, you cannot say carbon plus magnesium oxide. It will not react because carbon is less reactive than magnesium, so it will not displace it. It cannot react with aluminium oxide. So I cannot say aluminium oxide plus carbon because there will be no reaction, since carbon is less reactive than aluminium and will not displace it. So in this case, when we cannot use reduction with carbon, then we have to use electrolysis. So basically, the very reactive metals are obtained by electrolysis of the molten compound. Remember when we were talking about electrolysis, in the chapter of electrolysis, we said we could obtain sodium metal by electrolysis of the molten sodium chloride. So if I have molten sodium chloride and I do electrolysis, I get sodium. We're also going to use electrolysis to obtain aluminium. Now, those that are less reactive than carbon, these can be extracted by reduction of their oxides by the raw form of carbon, or one of the forms of carbon, which is coke. So coke is a form of carbon. I can react it with oxides of zinc or iron or tin, and that will help to reduce these to form the pure metals. Okay, so let's take a look at a typical question regarding this idea. The list gives the order of some metals and hydrogen in the reactivity series. Metal X is also included, so he put some sort of metal X there. Which row correctly shows the properties of metal X? Now, X is where? X is below hydrogen in the electrochemical series. And anything that is below hydrogen, will it react with acids? No, we said copper, for example, will not react with hydrogen because it is less reactive. So it does not react with acids, so my answer is A or B. Now, will the oxide of X be reduced by carbon? Well, where is carbon? You should remember that carbon is below magnesium but above zinc. So carbon is somewhere between magnesium and zinc. So that means that carbon is more reactive than X. So will it reduce the oxide? Yes, if the carbon is more reactive than X, then the oxide of X will be reduced by carbon, so my answer is B. Okay, so let us take a look at aluminium. What do we do to do extraction of aluminium? First of all, which method are we going to use? We said we need to use electrolysis. Why? Because we cannot use reduction, since carbon is less reactive than aluminium and will not displace it. So we need to do electrolysis. The other question is, what is the ore of aluminium? The ore of aluminium is called bauxite, and bauxite, you should know, is aluminium oxide 3 water, or it is what we call hydrated aluminium oxide. So the main ore of aluminium is bauxite. Now this bauxite has some water in it, so we heat it to remove the water and get pure aluminium oxide, or what is sometimes referred to as alumina, aluminium oxide, Al2O3. Okay, and then we said we need to do electrolysis. Now the next question would be, are we doing electrolysis of molten aluminium oxide or aluminium oxide dissolved as a solution? Well, we said if we dissolve aluminium oxide, we don't get aluminium, or if we dissolve the solution of an oxide of a reactive metal, then we don't get the metal, we get hydrogen. So in order to obtain the metal aluminium, we need to do electrolysis of the molten aluminium oxide. Now the problem is, in order to heat aluminium oxide until it melts, I need to heat it to 2100 degrees centigrade. So the melting point of aluminium oxide is very, very high, and that requires a lot of energy to melt the aluminium oxide. So we try to add some sort of impurity, and we should know that addition of impurities lowers the melting point. So they decided that, or scientists came up with, the addition of cryolite. So they found that if we add a little bit of cryolite, which serves as an impurity basically in the aluminium oxide, it will lower its melting point from 2100 to 900 degrees centigrade. So that is why the electrolyte that we're going to work with is molten aluminium oxide plus cryolite. If we're asked why is the cryolite added, we say first of all to lower the melting point of aluminium oxide. If we need another reason, it is to act as a solvent for the aluminium oxide. So it's as if I'm dissolving the aluminium oxide in the cryolite. Okay, electrodes will be made of graphite, which is the carbon. So if we're asked which substance is the electrode made of, we say it's made of graphite. But which element is the electrode made of? It is made of carbon. Okay, so this is basically what happens, and what we do is at the cathode, the aluminium ions, which are positive, go to the cathode, take up electrons and become aluminium metal. So the aluminium metal is collected at the cathode in the form of molten aluminium, of course, because all of this is at a very high temperature. Now at the anode, the other ion we have, remember we're doing molten aluminium oxide, so aluminium ions go to the cathode and the oxide ions go to the anode. Now when the oxide ions go to the anode, they give up electrons and become oxygen, which is diatomic. The balancing is as such: in order to have 2 oxygens after the arrow, we need 2 oxygens before the arrow, but that means that we have 4 negatives, so this is balanced with 4 electrons. Now the problem is we're releasing oxygen gas at an electrode that is made of carbon. The carbon electrode will basically burn in this oxygen that is being released, and it forms carbon dioxide gas, and that means that the positive electrode is being used up and will need to be replaced from time to time. So if we're asked why the positive electrode needs to be replaced from time to time, it is because it burns, the carbon electrode burns in the oxygen formed to give carbon dioxide gas. Okay, so this is a typical question about the extraction of aluminium. Name the main ore of aluminium. What was the ore of aluminium? Bauxite. Why does the molten electrolyte contain cryolite? We said, why do we add cryolite to the solution? We said to lower the melting point of aluminium oxide. That is the main reason. If he wants another one, then you can say to act as a solvent. Okay, oxygen is produced at the positive electrode. Name another gas which is formed at the positive electrode. Of course, we said when the oxygen is formed at the positive electrode, then the carbon electrode burns in the oxygen and it forms carbon dioxide gas. Okay, that's extraction of aluminium. Now, if we talk about the extraction of iron, you should realize that the extraction of iron can be done by reduction with carbon, because iron is less reactive than carbon, so it can be displaced by it. Okay, this extraction of iron is usually made in huge furnaces, which we call the blast furnace. So the blast furnace is sort of a huge building. At the top we add what? We're going to add coke, limestone, and hematite. These are the three substances added to the furnace, and they're added from the top. Now from below we introduce hot air on all sides of the blast furnace so that the hot air rises to meet the substances that are added. Now inside the blast furnace there are three main reactions that occur. The first reaction that happens is the coke coming down burns in the oxygen that is present or that is introduced, and this forms carbon dioxide gas. Now you should realize that any combustion reaction or burning reaction is very exothermic. So this first reaction helps to raise the temperature of the furnace and give enough heat for the other reactions to work. Now the next reaction that happens is that we have formed carbon dioxide gas, but then we still have a lot of coke. So this coke reduces the carbon dioxide to carbon monoxide gas, and it is the carbon monoxide that is used to reduce the iron oxide or the hematite. So we have introduced hematite, and we said that hematite is Fe2O3. So remember that this is the ore of iron. So the ore of iron is hematite. Okay, the carbon monoxide reacts with the iron oxide, which is the hematite. This forms iron, and the carbon monoxide is changed into carbon dioxide. Notice that at the top of the blast furnace there is an exit part for the waste gases. So any extra carbon dioxide gas or carbon monoxide or whatever will be released from the exit for the waste gases. Okay, so the iron formed in that third reaction will settle at the bottom of the blast furnace because iron is something with a very high density. But notice that we have added three things at the top of the blast furnace. We added the coke, which was burned in oxygen to give carbon dioxide, and then the carbon dioxide reacted again with coke to give carbon monoxide. We also added hematite, and hematite is the ore of iron. So remember that the ore of iron is hematite, and hematite is the Fe2O3 that was reduced by carbon monoxide to give iron and carbon dioxide. Now there is something else that we added, which is the limestone, and we haven't mentioned why did we add the limestone. Well, let's take a look at the limestone. The role of the limestone in the blast furnace is to remove impurities, and you should remember that the hematite is something that is a raw material obtained from the earth. So when you dig up something from the earth, the main impurities is sand or soil. So what happens is the limestone is actually calcium carbonate, and you should know that limestone is calcium carbonate. Now in the heat of the furnace, the limestone breaks up and forms calcium oxide. Remember when we were talking about carbonates of metals? When we heat them, they give the oxide plus carbon dioxide. So calcium carbonate, when it is heated in the blast furnace, it becomes calcium oxide plus carbon dioxide gas. The lime is calcium oxide. So remember that calcium oxide is called lime. This lime reacts with the main impurity in the blast furnace, which we mentioned is sand, and the chemical name for sand is silicon dioxide. So the lime, calcium oxide, reacts with silicon dioxide, and what comes out is calcium silicate, and calcium silicate is referred to as slag. Now in the blast furnace, this slag floats on top of the iron. So actually it is a very important product. In the blast furnace, it floats on top of the iron, and that helps to prevent the reoxidation of the iron. If I expose the iron to the hot air that is going in, then it will be reoxidized. So presence of the slag on the surface of the iron prevents its reoxidation, and then it can be removed later from the blast furnace and used in road making. Remember, there was one other substance that we said we use in road making. Do you remember which one? The one we obtained from fractional distillation of petroleum or fractional distillation of crude oil. The last fraction at the bottom was called butadiene, and butadiene is also used in road making. So slag is used in road making too. Okay, now the iron that comes out from the blast furnace is not pure iron. It still has a lot of impurities like carbon, sulfur, phosphorus, silicon, and so on. And we need to get rid of this, and then we convert it into the kind of steel that we need. So the molten iron that is obtained in the blast furnace is placed in another sort of furnace, and hot oxygen is bubbled through it. So when the oxygen is bubbled through it, it oxidizes the impurities. Now, what are the impurities that we talked about? We said it would have some carbon. So when you pass oxygen through it, the carbon becomes carbon dioxide gas, and the gas escapes. We have some sulfur, because coal has some sulfur impurities. So when you put coke in, there is sulfur impurities in it. So when we pass oxygen here, then the sulfur forms sulfur dioxide, and that is a gas that escapes. But some of the other impurities like silicon and phosphorus will actually form acidic impurities. So acidic oxides. So this acidic oxide, we add to it calcium oxide, which is a base, in order to react with it and neutralize it, to remove it in the form of slag. So it forms slag that floats on the top of the furnace, and it can be removed. Then we take the iron, the molten iron from that process, and we add to it the specific amount of carbon or other metals like nickel and chromium, in order to make the specific kind of steel that is required. Remember, we said we have different types of steel like mild steel and stainless steel. Okay, let's look at a typical question about this part. 4 reactions that take place in the blast furnace to produce iron are shown. Which reaction is used to keep the furnace hot? Remember, we said which of the reactions is exothermic and helps to raise the temperature of the furnace. Remember that is that first reaction between the coke and oxygen to form carbon dioxide. Okay, state 2 functions of the coke used in the blast furnace. We added coke. What does it do in the blast furnace? It provides heat, since it burns in an exothermic reaction, and it forms carbon monoxide that actually acts as the reducing agent of the ore. Okay, another question. Molten iron from the blast furnace contains impurities. The process of turning the impure iron into steel involves blowing oxygen into the molten iron and adding calcium oxide. So that's what we just talked about. What are the reasons for blowing in oxygen and for adding calcium oxide? So when we're trying to purify the molten iron, why do we blow in oxygen? Because the choices that we have are carbon is removed by reacting with oxygen, or because iron reacts with oxygen. No, we put oxygen not to react with the iron, but to react with the carbon impurity and remove it in the form of carbon dioxide. So my answer is A or B. Why do we add calcium oxide? Remember that we said some of the impurities form acidic oxides. So I put in a base to react with it. So it reacts with acidic impurities, making the slag that will float on the surface of the iron. Okay, so my answer is A. Iron is extracted from hematite in the blast furnace. The hematite contains silicon oxide sand as an impurity. What reacts with this impurity to remove it? We said, what do we add to the blast furnace in order to remove the sand? We add what? We add calcium oxide, because the calcium oxide is formed from the limestone that we add. Okay? Another question. Steel is made by adding what to molten iron? To remove what from the iron? Steel is made by adding oxygen to molten iron to remove what? To remove carbon. That's right. Okay, so it is to remove carbon. Now, stainless steel is what? It is more resistant to corrosion than mild steel. Remember that stainless steel has, in addition to iron and carbon, it has nickel or chromium, which helps to make it more resistant to corrosion. Okay, extraction of zinc. First of all, how are we going to extract it? We're going to extract it by reduction because zinc is less reactive than carbon and can be displaced by it. Okay, what is the ore of zinc? The ore of zinc is a substance called zinc blende, and zinc blende is zinc sulfide. So if I'm going to react something with coke, I want it to be in the form of oxide so that it's going to be an oxidation reduction reaction. So we need to change the zinc sulfide first into zinc oxide, and then I reduce with coke. So how do we change zinc sulfide to zinc oxide? It is roasted in air. Roasted in air. Don't say reacts with oxygen. It is roasted in air. Okay? So zinc sulfide, when it is roasted in oxygen, then it gives the zinc oxide plus sulfur dioxide. And you need to balance the equation as shown. Then we take the zinc oxide and put it into a sort of blast furnace also and add coke to it. So we just put into the blast furnace zinc oxide and coke. We do not add any limestone. This is because the zinc oxide will react with the coke to give zinc. But this at the very high temperature of the furnace, because we're introducing hot air from the bottom of the furnace, the zinc has a relatively lower melting point, so or boiling point, so it evaporates and collects on the sides of the furnace. Can you see where the zinc is collected? So we do not need to sit down and purify it. It's already purified in that at the high temperature of the furnace it evaporates and condenses on the sides in a separate area that from which it can be collected. So the zinc forms vapors that rise to the top of the furnace and condenses in these side pans. The other reaction would be extraction of something like copper from its carbonate. So in some cases we will be asked to obtain copper from, for example, copper carbonate, or obtain lead from lead carbonate. It will be exactly the same process. So if we start with copper carbonate, how can we get to copper? This is actually one of the methods, and then we will discuss a different method. But this is one method to obtain copper from copper carbonate or lead from lead carbonate. So we get the carbonate, and we should know that copper carbonate is green. Place it in an evaporating dish in this two double-ended tubes or open-ended tubes, and we heat it. When the copper carbonate is heated, it forms copper oxide, which is a black solid, and the carbon dioxide formed will simply evolve. So now we have in the evaporating dish, the copper carbonate has changed to copper oxide, which is a black solid. Then hydrogen gas is passed over the heated copper oxide. When hydrogen reacts with copper oxide, it changes the copper oxide into copper, and the hydrogen changes to water. So we said this is a redox reaction. The copper oxide in the evaporating dish becomes copper, and that means it becomes reddish brown solid, and the water that is formed will pass through the U-tube that is in ice, so it will condense and to form water liquid in that U-tube. Any excess gases are allowed to escape from the other end of the U-tube. So this is one method in which we have changed the copper carbonate to copper oxide, and then the copper oxide to copper, and we end up with copper in that evaporating dish. Another method would be this one. So here he had something called malachite, and he's saying malachite is actually a mixture of copper carbonate and some insoluble impurities. And he's saying obtain the copper from the copper carbonate solid. So what should we do? We could take the copper carbonate, crush the malachite first in a mortar and pestle. Remember that copper carbonate is green in color. So crush the malachite in a mortar and pestle, add dilute acid, any acid, so let's say sulfuric acid, to the solid malachite in a beaker. Remember that any carbonate with acid will form a salt plus carbon dioxide. So the carbonate reacts with the sulfuric acid, it dissolves to form a blue solution of copper sulfate. Any impurities will remain in the beaker. So he's saying we had copper carbonate plus impurities. So now we want to get rid of anything that we don't want. We filter through filter paper and funnel to remove the insoluble impurities. Now we have a solution of copper sulfate. Now what do we do in order to get copper? Well, we could do a displacement reaction. Remember that we said if we add a more reactive metal, it will displace the less reactive metal from its salt. So if I add magnesium powder to a solution of copper sulfate, then the magnesium will react to form magnesium sulfate and copper metal will be formed, so a brown precipitate will be observed. Then we filter through filter paper and funnel. We obtain this brown precipitate of copper as residue, wash the residue with a few drops of distilled water and dry between two filter papers. So now we have the copper metal. Okay, that's the end of the extraction of metal. So please study this and try to do as much of the questions as you can, and we'll meet in the next